Thank you, Irene, for the introduction. And hello, everyone. Welcome to this episode of the GenScript webinar series. As Irene kindly mentioned, my name is Josh Wang. I work in the R&D team of GenScript in the Seattle area. Today, I'll be telling you a little bit about a few NGS products that we are really excited to launch really soon. The topic of my presentation today is advancing genomics, medicine, and health together. Here's what I plan to talk about in today's webinar. I will start with a short introduction and overview. I will then cover our NGS library preparation solutions, a two-pronged approach, and our hybridization capture NGS target selection solution based on our unique semiconductor DNA synthesis technology. Lastly, for all of the products that I will talk about, we are welcoming early users as beta testers and collaborators. So please feel free to reach out to us if anything in this webinar interests you. Since you're here, I believe you have already known GenScript to some extent, but I still would like to quickly show this history of the rapid growth of GenScript, like what I do for basically every other presentation I give internally or externally. It just reminds us how far GenScript has come along and how we became trusted by our thousands of customers. It makes us humble and work even harder to get things done for them. GenScript was founded back in 2002 in New Jersey with a focus on gene synthesis services. Since then, GenScript has been in this fast growth mode. Not only has GenScript expanded geographically around the globe, like in Asia Pacific, Europe, and of course in the Americas, we have also enlarged our service areas from making genes to oligo services, especially regulated oligo services, protein and peptide services, antibody production services, and basically all biological research reagents across the board. GenScript became public in 2015, and that fueled our accelerated investments in science and technology. For example, GenScript acquired Custom Array, a long-time and highly respected company in oligo array business in 2017 to facilitate our diagnostic oligo product line. At GenScript, we have always committed to bringing experience and expertise to the research communities to provide researchers with the best services and products that they deserve. We are now serving more than 110,000 customers globally, and we are the #1 gene synthesis service provider in the world. One area we have recently entered, as you can see on this timetable, is the next generation sequencing reagents field. That will be the focus of my presentation today, and I will talk more about them in detail later in my presentation. On this timetable, you can also see towards the end that GenScript has been trying to help with COVID-19 research and testing since its onset. Unfortunately, almost 10 months in, we are still in this global pandemic. So before I move to NGS, I wanted to remind everybody that we have worked with COVID-19 researchers from early on and have accumulated a lot of experiences with helping them. So COVID-19 virus, or the SARS-CoV-2 virus, the virus that has led to over 1 million deaths worldwide among more than 38 million infections, has been really having an enormous impact on the world's economy and people's lives. For all of us at GenScript, we were probably among the first to really see and feel the impact of COVID because we have a large operation in China where the first cases were reported. To us, the battle has been both for public health and personal. And because of that, we have committed a lot of energy and resources to fighting this COVID battle. And this is a summary of the related work we have done or we are currently doing. We have come up with 2 distinct ways of doing virus detection ourselves, one qPCR-based and the other neutralizing antibody-based. And we also have been doing what we do best, which is to provide custom biological reagents to researchers, including reagents like cell lines, peptide libraries, recombinant proteins, GMP-grade plasmids, and so on and so forth. There are a lot more details on each of these items on our website with a lot of educational materials that we have collected and created as well. So please take a look over there if you're interested in anything, or just reach out to us if you have any questions or inquiries. Now COVID will pass one day, hopefully very soon. Let's move our attention to things that impact health and healthcare in much longer term. That will bring us to next generation sequencing, or NGS. I'm sure you have all heard of NGS before, and many might be very familiar with it. NGS has been instrumental to many research fields and led to numerous seminal findings. But to me, the potential that NGS holds in diagnostics and therapeutics in the future is even more exciting. At the very least, without mentioning a lot of the fancier diagnostic applications many labs are working on, NGS by itself is a powerful tool to search for mutations, especially those that are of low frequency or in a heterogeneous population of cells or background. And NGS is also a powerful tool to do that in a large population very easily. When it comes to mutations and diseases, and really genetics and diseases, not only does NGS enable detection of harder and rarer mutations, or in other words, detecting more deeply, it also provides the possibility of reviewing information more widely, or in other words, it provides bigger pictures of the individuals by surveillance of their genomes. The hope here is that we move from symptom-driven medicine, which was universally used in the past for the whole population around the globe, and also move away from clinical trial-driven medicine, where selected individuals or average patients got to represent the whole population, to a new state where we could perform more comprehensive diagnostics, and based on that, precisely treat individuals based on their genetic code and sophisticated prediction algorithms. That's what many people refer to as precision medicine. The first step, however, for all of this to be even possible is actually sequencing and deciphering the genetic codes. I won't expand on them, but there have been some areas where NGS is already used heavily towards precision medicine. As an honorable mention, in the US, the White House launched the Precision Medicine Initiative 5 years ago in 2015. And the goal of this initiative is to ultimately be able to treat the right patient with the right drug at the right time with collected information, part of which will be sequencing information. For NGS to work, or for anything to work, there is a basic principle and a basic workflow. Fortunately, the principle and workflow for NGS is not very complicated. Let's do a quick review. I want to acknowledge that there are quite a few platforms that could be used to do NGS, or more accurately put, massively parallel sequencing. But for today, I will focus on those platforms offered by Illumina, the dominant player in this space. Here is a lineup of Illumina sequencers. Some of them are outgoing, but they basically vary in size and the amount of sequencing data they are able to generate. But all of the instruments use the same underlying chemistry, which is very similar to Sanger sequencing chemistry, and it's called sequencing by synthesis. Briefly, it starts with NGS library preparation, a process to attach specific sequences to DNA samples so that they can be amplified and subsequently read by the sequencer machine. After the specific sequences are added or the library is made, one can select part of this library if not every molecule is desired to be sequenced for considerations like savings of overall costs, sequencing the interested regions more with the same number of output reads. This pertains to target selection that we will come back to at a later point in this talk. Next, these made library molecules, either raw or selected, are loaded onto a carrier called flow cell, where bridge amplifications happen. This process copies the DNA library information onto the flow cell through the sequences attached in the first step. A flow cell contains millions of positions, or officially called clusters, for library molecules to land and get copied on. And this process provides the massive parallelization for NGS. Next is the sequencing step. The copied DNA on the flow cell serves as the templates for Sanger-like reactions to happen, and DNA sequences are read from each spot or cluster on the flow cell. Last is to transform the reading from the machine to nucleotide information and start to form scientific analysis, scientific hypothesis, and scientific conclusions. With this quick review of NGS 101, I wanted to introduce to you what our team at GenScript can help you with for your NGS-related research and applications. As I mentioned in the very beginning, GenScript has a long history of making industrial-level synthetic reagents, nucleic acids, proteins, and so forth. So we felt obligated to put our expertise to work and to help our customers overcome some of the difficulties that still exist in NGS and targeted NGS applications. We are currently offering whole genome NGS library preparation kits for Illumina platforms. We offer two chemistries to make NGS libraries, both of which are well-established methods, but we have invested and found our own ways to have optimized them and made them more consistent and affordable. We also offer target enrichment solutions, both PCR or amplicon enrichment and probe or hybridization capture enrichment. I will talk more on the hybridization capture side of things later in this presentation, which is using biotinylated DNA sequences or probes to pull down genomic regions of interest by sequence Watson-Crick complementarity and biotin-strep-avidin interactions. We are offering a novel solution to making hybridization capture probe, which is based on a core and proprietary technology at GenScript. I will also show you 3 innovations that we have included with our hybridization capture probes and its accompanying kit. Moving on to specific product offerings, here is an overview of what GenScript offers for NGS library prep. As I mentioned, we offer 2 kits with 2 chemistries. They are both listed here, and they are called GenTrack library prep, which is the one on the left, and GenNature library prep, which is the one on the right. In its essence, library prep is to make DNA in a form that's compatible with the sequencer by having the components to be recognized by the sequencer. GenTrack, the one on the left, is a method that adds such components by a ligation step. It starts with fragmented DNA, which can be generated by physical or enzymatic means. Adapters that contain Illumina sequences and simple markers or simple indices are ligated onto such DNA fragments. An optional amplification step can help increase the quantity of libraries for certain cases. For example, if the starting DNA quantity is very small, or the library needs to go into a target selection process like a hybrid capture step. GenNature, the one on the right, is a method that adds sequencer recognizable components by transposase. It takes advantage of an enzyme that cuts the DNA while ligating DNAs onto the cut site. This is followed by an amplification that completes all the necessary components needed for sequencing. It is also known as a tegmentation-based method. Both GenTrack and GenNature have integrated a series of components we have come up with in-house, engineered in-house, and manufactured in-house. Let's focus on GenTrack for a minute. Like I mentioned, GenTrack is a ligation-based method. You may have noticed that it's called GenTrack 2.0 or 2.0. This 2.0 is relative to a previous version we had where DNA samples had to go through sonication fragmentation before they can be subjected to GenTrack library prep. For 2.0, we have expanded our capabilities. As is shown on this table, in addition to what we had before, which was prepping with sonication fragmented DNA, we have introduced not only an enzymatic fragmentation module, which contributes to GenTrack 2.1, but we have also included a repairing module, which contributes to GenTrack 2.2. They work off the same principle, but they differ so that each unique application and each unique sample type can be better accommodated. For applications that involve shorter DNA to start with, like in the case of working with PCR products or cell-free DNA in liquid biopsy applications, a non-fragmentation or a sonication fragmentation is better than an enzymatic fragmentation. One can just go with GenTrack 2.0. If one is working with degraded FFPE DNA samples, GenTrack 2.2 might be better as it has a DNA repair module. As of the quantity and quality of the libraries made with GenTrack Kit, we have generated a lot of data on it internally. I'm not going to show them all to you, as you will soon see more data from our customers with more real-world examples. But I do want to highlight the fact that I just mentioned, which is that you are at freedom to choose the right configuration of modules that fits your use case the best. Here I'm showing you a couple of data of libraries made with 1 nanogram of DNA of different sources. And these sources are high-quality genomic DNA, cell-free DNA, and medium-quality FFPE DNA. They have undergone different modules per our discretion as the best fit for them, as you can see. GenTrack 2.0 for genomic DNA, 2.1 for cell-free, and 2.2 for FFPE. On the left, I'm showing you the yields of libraries made after following standard protocols of GenTrack and another vendor, vendor K, a well-known vendor, although their kit is not modularized. GenTrack shows consistently better yields in all cases. And in terms of retaining DNA complexity, which is very critical for low input DNA, as is the case here for 1 nanogram DNA samples, GenTrack is also doing excellent. As shown on the right figure, when assigning the same number of sequencing reads to libraries made on the left, GenTrack libraries have consistently lower duplicate reads than vendor K's, indicative of higher molecule diversity. Speaking of molecule diversity, it's hard not to mention unique molecular identifiers, or UMIs. Researchers use UMIs to maximize the recognition of unique molecules for applications in variant detection, transcript counting, and so forth. As you can see, we have made UMI-ready adapters for GenTrack libraries, perhaps 2. This is part of GenTrack 2.3 listed here. Just to expand on adapters a little more, since we are on this important topic already, adapters play a really critical role in the success of NGS library prep, therefore play an important role in the whole NGS experiment. Adapters are important for sequencer reading, for sure, but more importantly, it could be a source of biases and failures. Say if the sample indices contained by the adapters are poorly designed or poorly made with a lot of contaminations in them. This would lead to misassignment of reads to the wrong samples, leading to false results. Also, bad adapters can hurt ligations too. Say if the adapters contain oligos with truncated sequences. For all of these reasons, here at GenScript, we take making good NGS adapters very seriously. Here are some stock adapter formats we offer. Single index adapters, unique dual index adapters, where we offer up to 8,000 pairs of unique dual index designs. Dual index adapters with EMI components. When it comes to custom adapters, we just really strive to meet all requests from our customers, no matter how easy or how difficult a case may be. Really, it's about what you need to make your work easier more than anything else from our perspective. No matter whether it's on-shelf stocked adapters or custom-made adapters, we have set up a complete procedure and QC to guarantee high quality. Here I'm showing you a couple of things we look at for our adapter production. On the left, you are seeing a Caterpillar gel electrophoresis report of an oligo used for NGS adapters. It has a purity of over 99%. This ensures good ligation to your DNA sample and amplification efficiency if amplification is necessary. On the right, you're seeing a mass spec plot where I'm showing you that the adapter molecular weight measured by mass spec matches exactly as its theoretical weight, indicating that there is no error or no misincorporation of incorrect nucleotides in the manufacturing process. This, again, maximizes your opportunity to make good and successful sequenceable libraries. On top of quality and purity of each individual oligo, the correctness of the sample indices within the adapters is also very important. Sample indices, as you know, they are used to differentiate sequencing reads of one sample from those of another sample after sequencing. I mentioned single index, dual indices, unique dual indices a couple of slides ago. They are just different ways and different rigors of doing this read assignment job. So any mistakes in that assignment process could lead to false results, especially in rare mutation detection. So obviously, it is critical that assembly indices are not in any way mixed up at the synthesis step. Here I'm showing you a figure which is the one to the left. It's provided by one of our customers. It shows the rate at which they detect sample index contamination from our adapters versus adapters from another vendor whose oligos are also of very high quality and purity. You can see that the GenScript adapters have a much lower cross-contamination rate, and for that reason, we are setting our quality control standards for adapters cross-contamination rate at 0.1%. That is 5 times lower than the industry average standard, which is at around 0.5%. In addition to this data that our customer provided us, we also do a quarterly monitoring of the cross-contamination rate of our adapters, as is shown on the figure on the right. This rigorous monitoring really ensures that our qualities are consistent and are consistently high quality. In addition to extremely low cross-contamination rate, we also offer adapters for specialty uses and with various modifications. Unfortunately, I don't have all the time I needed to tell you all of them today, but we list a lot of them on our website, so you're very encouraged to check out our website or just reach out to us for more information. Moving from adapters back to library prep, I would like to briefly touch on our GenNature kit. It is also a second and upgraded release of this product line. Compared to 1.0, GenNature 2.0 has been optimized in multiple areas, especially the enzyme, the tegmentase activity aspect. It is now compatible with picogram DNA input. GenNature is great for making NGS libraries from genomic DNA, plasmid DNA, PCR products, and it is super easy to automate with various liquid handler platforms as well. When it comes to the performance of GenNature 2.0, I'm again just giving you a couple of highlights. Figures on this slide compare GenNature 2.0 and another segmentation-based library kit offered by vendor I. A great kit a lot of researchers use. On the left, I'm showing you the library yields. You can see no matter whether it's plasmids or genomic DNA, no matter whether it's low input or normal input, or GenNature kit outperforms vendor I by actually quite a significant margin, fourfold in some cases. That speaks to the efficiency of our enzymes and buffers that we have engineered and produced. The figure on the right looks at the percent of reads that are deemed to have a soft clip bases towards their ends. Soft clip bases are basically bases that the sequence aligner cannot recognize in the reference genome. As I mentioned, GenNature, similar to other similar kits like vendor I's, uses a segmentase to break DNA into fragments and add necessary sequences to those breakpoints. If the breaking events have problems, it may show in the sequencing data that bases at or near the breaking points are incorrect, and therefore they cannot be assigned back to the reference genome. This figure on the right really depicts that. As you can tell, GenNature 2.0 has a lower percentage of reads that contain soft clip bases across the board, no matter the sample type, no matter the sample input. This indicates a more accurately acting enzyme, and this also provides max likelihood of good fragment ends to your DNA sample. All of this despite the higher efficiency of the enzyme. Here's a summary of our NGS library GenSolutions. We have GenTrack and GenNature kits. They use different chemistries. The choice between them depends really on your application, your sample type, your automation requirements. But they both come to you with high quality design and high quality manufacturing and the backing of GenScript experience and expertise. Now I would like to focus on NGS target selection. As I alluded to in the beginning of my talk, sequencing only a selected portion of your NGS libraries might be beneficial in many cases for reasons like cost saving, ease of operation and analyses, or even just for reality. For example, if an actionable cancer mutation is present in the patient sample at 0.5% frequency, it requires, I'd say, at least 500x coverage depth at that particular position to make a reliable mutation call for diagnostic purposes. It would be just next to impossible to do such a deep coverage if we do whole genome sequencing at the current time. So amplicon and hybridization capture are two most used ways of selecting NGS targets, and we at GenScript offer both. For today, I will focus more on hybridization capture. We call our hybridization capture system GenFisher, and the probes are called GenFisher probes. The principle and workflow is actually not complicated either. As shown here, we start with NGS library molecules that are hopefully made with either GenTrack or GenNature library kits. Say we have two molecules here, the blue fragment 1 and the gray fragment 2. We introduce to the system a GenFisher probe, which is a biotinidase probe that carries the sequence that's complementary to the library molecule that we are interested. For example, the blue fragment 1 here, after capturing with beads that have strep evidence and washing away the rest, we are now left with only the blue fragment 1. We can then just sequence it without wasting any good sequencing to the stuff we don't want, like the gray fragment 2. Imagine there are many targets that we are interested. The only thing that we need to do in addition to what we have done here is to put many more GenFisher probes into the capture system, right? So what's really critical in the system then is these probes. They determine how easily and how efficiently this capturing or this fishing process works and performs. Our GenFisher probes, different than basically everybody else, are made in a special and proprietary way. It is based on a core chip DNA synthesis technology that has been proven and validated by time in the past almost 2 decades now. This core technology is GenScript's semiconductor DNA synthesis technology. It is very similar to the technology used to make computer chips, cell phone chips, and other electronic devices. It enables us to synthesize thousands of oligos on these chamber-enclosed platinum macroelectrodes on the chip all at once. The chips come from silicon wafers, and they are placed on slides to fit into our synthesizers. The synthesizers then controls the electricity passing through the chip. It actually controls each of these electrodes on the chip. By doing this, we are able to select the chambers to be activated or deactivated by just controlling the flow of electricity. Therefore, we can precisely and confidently grow only the oligos that we intend to grow on these microelectrodes. Currently, there are 2 chip sizes that we are offering to synthesize oligos on. One has the capacity of growing 12,000 oligos, and the other 92,000. A third one with 100 times those capacities is on its way. So we are really excited about what we will be able to revolutionize with this awesome technology. With that, let's take a look at what the synthesis quality is. Here I'm showing you a distribution of oligos synthesized on our 12,000 oligo chip. They were 125 nucleotides long. The synthesis was completed in a business week and was subjected to Illumina NGS quality control. The figure shows you the NGS results, where the x-axis is the number of NGS reads each made oligo received, and the y-axis is the number of made oligos. Basically, the narrower the distribution, the more even number of NGS reads each made oligo was getting, the more equal the amounts were among oligos. You could see that all 12,000 oligos are quite evenly distributed. The NGS data also suggested that we were able to detect 99.74% of all the oligos we intended to make, with an average error rate of 1 in 370 bases. The interdecile ratio, which is the NGS coverage of the made oligo at the 90th percentile over that of the 10th percentile, is 1.98. This number is a common way of monitoring the uniformity of oligo pools. Just as a reference, an oligo pool typically is considered uniform with a high single-digit measurement of this metric. So we were very pleased to report a number that's close to 2. That's really a step up from any previous technology. And again, here is a summary of what we believe contributed to the efficiency of our synthesis and what we can do with it. The CMOS semiconductor technology, the precise controlling, the closed chamber, all contributed to our good uniformity, our production efficiency, and our cost effectiveness. Now let's refocus on NGS and see how we are applying this awesome semiconductor technology to target NGS. The core of this is, of course, the probes that match the sequences of the genome that are of interest. Naturally, we do this synthesis of sequences with our chips. Here is what we do. Starting from the very left of this diagram, thousands of molecules that carry the probe information are made in parallel very quickly and precisely by the chip technology I just talked about. After they are removed from the chip, they are subjected to PCR with biotinylated primers to become actual target enrichment probes. At this point, these biotinylated probes are ready to hybridize and capture with pre-made whole genome NGS libraries, which will then give rise to selected targets for subsequent sequencing and analyses. Since our semiconductor chip synthesis gives really uniform and accurate oligos, as I showed on the last slide, the resulting NGS target selection panel coming out of this process will inherit that uniformity and accuracy as well. This will then translate to strong and even capture of the regions of interest. Now let me show you an example of that, but I wanted to show that with the context of having some other capture probe technologies side by side as listed at the bottom of this slide. As far as I know, this list covers all of the most seen and used tags available on the market. These probes can be single-stranded DNA probes. They can be RNA probes that are transcribed from synthesized and cloned DNA. They can also be double-stranded DNA that's made either by inkjet DNA printing technology or the semiconductor technology I've been talking about. I won't go into details of each of them, but they all have their unique pros and cons. With that in mind, let's look at this piece of data. Here I'm showing you how the GenFisher probes capture compare to capture pools made with other technologies. The panels from each provider targets the exact same 800 kb region in the human genome, and the experiment was performed based on the recommendations provided by each provider. The x-axis again shows the various providers and their technology, and the y-axis shows the capture efficiency measured by the on-target base percentage that is defined as the percent of sequenced bases matching the desired target regions. The blue bars show the raw on-target percentage, while for the orange bars, we'll consider a base as an on-target base if it's within the 150 nucleotides tagging region of the target. Because, the NGS library molecule may overlap only partially with the probe for it to be duplexed with the probe and pulled down by the probe. As you can see for this specific capture panel, the probes made with GenFisher Semiconductor technology provided the most efficient capture performance with a padded on target of close to 90%. Comes next is the single-stranded DNA probes with a pretty strong performance as well, at around 80% on target. Others gave variable but significantly worse capture performance. We acknowledge that the differences in capture performance will vary with the target regions, but we do believe that this comparison still demonstrates that our semiconductor synthesis technology used for NGS probes is an excellent solution to NGS target selection. Here I'm showing you the uniformity performance of our GenFisher probes. In this figure on the left, the x-axis is the coverage depth, and the y-axis is the percentage of bases covered at that certain depth. A uniform capture would show consistently high percentage above a certain coverage depth and a steep drop below that coverage, as is the trend shown in this figure. Vendor T here is a recognized leader in creating uniform NGS capture pools. As you can see, GenFisher panels closely match to it. The figure on the right is showing the comparison of capture efficiency at per probe level for two independently synthesized GenFisher capture probes. The near perfect diagonal trend line there really shows that our semiconductor synthesis and subsequent manufacturing process of the GenFisher probes guarantee high batch-to-batch consistency. As much as we are confident in our capture technology, we understand that it's not perfect, just like every other technology. We believe for each target enrichment panels out there, improvements can be made in areas like probe design, probe uniformity, probe concentration fine-tuning, and towards them, supplementing small numbers of probes at desired amounts, or many refer to as probe spike-in, would help. But not every technology offers the opportunity to do that optimization easily. Here I'm showing you what I think will make this improvement process very easy if one decides to do that. That would be a combination of capture probes made by chips, like I described, and combine that with probes that are made by the more conventional and old school way of columns. I didn't bring this up earlier, but GenScript has a mature system for column oligosynthesis at scale as well. Some numbers are shown here, or daily and yearly capacity and or certification situation. Since we as scientists have access to the two worlds of chip and column oligos, we of course did a study where we studied how compatible they are in captures. Here I'm showing you the data on the right. The blue bars here show the non-padded on-target percentage, and the orange dots show the 30x plus coverage depth base percentage, another metric for capture uniformity. The first data point is a panel of 8,000 probes solely made by the semiconductor chip technology. And the second is the same probe set, but with a combination of 80% probes randomly selected to be made by a chip, and the remaining 20% made by columns. The third data point is the same as the second one, except that the remaining 20% was made by a second chip. As you can see that all three ways of making and mixing probes gave nearly identical results, indicating that spiking additional probes into a working system is feasible and does not have a negative impact on the system. In fact, when we look at the number of probes that contributed to poor capturing, with fine-tuning this panel with single-stranded DNA spike-ins, we were able to reduce the number of poor capture regions by almost threefold. That, in the end, will result in even NGS coverage and likely a save in sequencing cost. So one route we have been recommending to our customers is to synthesize a panel with our chip technology, which is really fast and inexpensive. If there is an additional need for probes, whether it's for more coverage or more concentration, supplement in column probes because they're quicker and easier to make when the number of oligos required is low. When the design is fully locked down, we can make the entire final panel again by chips. With our combined technologies, this entire process of optimization and finalization could still potentially be shorter in terms of the time it takes if you get the same initial panel from other vendors with other technologies. This combination of probes of two different technologies unique to GenScript, as I mentioned. What's also unique is our new hybrid capture kit that allows for a much shortened workflow compared to offerings from others or from our own last generation offering. We have heard from our customers that they would love to see NGS target selection by capture be done in a single day rather than a 2-day process with the 16-hour wait time between library making and sequencing. So our customer voiced, we heard, we also acted. So we have engineered quite a few components in our GenFisher hybridization wash kit to realize this feature that I'm showing here. The most important thing for us while doing this work is to make sure selection performance was not in any way negatively impacted by the shortened time. Like many others who have tried this has seen before. I'm showing you 3 metrics here on this slide, and they were generated with the same panel as you saw on the last slide, that 8,000 probe set. When comparing the 16-hour HYPE data with the 1-hour HYPE data, we didn't see statistical significant differences between them in areas in on-target base percentage, 30x coverage base percentage, or greater than 0.2x mean coverage base percentage. This indicates equal performance among these 2 procedures. So it's really up to the customers to choose what workflow they want to use, and really the maximum freedom is what we are trying to offer our customers. Lastly, I wanted to talk about our GenFisher universal blockers. In hybridization capture target sequencing studies, permissive interactions between library adapters and target probes and adapters among themselves lead to undesired and wasteful sequencing. As you can see on this figure, doing the capture with or without the blockers show significant differences on target sequencing. Just as a note, since the libraries made with GenTrack or GenNature libraries prep kits have different chemistries and different DNA sequences, so the universal blockers that bind to them are also of different compositions too. This figure was done with GenTrack libraries and GenTrack compatible blockers, but we have seen a similar pattern with GenNature libraries and GenNature compatible blockers when it comes to the importance of having blockers in the capture reactions. That's something that's really not new. I think every vendor of capture probes has their solution of blockers, but our NGS universal blockers are really special compared to the previous ones. They are really carefully designed and dedicated engineered to minimize the interactions that I've mentioned just now to help optimize on-target sequencing. The proprietary modifications on our universal blockers make them compatible with any adapter design and any index length. And it also offers a strong binding between the blocker and the desired regions to be blocked. The figure at the bottom shows that our universal blocker solution is agnostic to the length of indices. This is, at this point, is really becoming more and more important as people are moving to longer and more diverse indices as the throughput of sequencers increase. So with GenFisher universal blockers, it's really a one-size-fits-all kind of scenario. So our customers don't have to struggle to pick the indices that they need to have for their particular set of blockers, or they don't need to spend the time to study which blockers would work for their adapters. So really making the life for a lot of researchers easier. So that's almost all what I wanted to talk about today. I've covered quite a lot of ground today. To summarize, I talked about our two-pronged solutions to NGS library preparation to offer flexibility pertaining the applications you have in mind and the sample types you may have. I've also talked about GenFisher hybridization capture probes and the kit, and how we have engineered it to accommodate faster workflow. The probes that are made with our Semiconductor DNA synthesis technology, or GenFisher probes, are really a superior way of doing target selection. One thing that I didn't get to talk about today is our AI probe design tool, where we have build a model to optimize the chance of capture success by designing the probes against your target regions to the best extent possible. I covered our proprietary universal blockers and how compatible it is with any index length. Lastly, as a component of library prep kits, we offer highly customizable adapter services. And with that, I would like to thank everybody for your attention. Thank you very much for registering and attending the webinar today. We look forward to seeing you again in our next webinar. Thank you and have a great day.